We finally come to the end of equilibrium when we discuss KSP. KSP is an equilibrium expression that helps us understand the dissolving of a solute in a solvent. KSP stands for the solubility product constant. It indicates how soluble a solid, generally a ionic compound, is in water. All right. If a KSP value is very small, that means that it's not very soluble. If it's very large, it is soluble. Even substances that are considered insoluble, that means that you look it up on a chart and it says it's insoluble, it has an S next to it in parentheses, it will dissociate to a small extent. Equilibrium just lies very far to the left. So if we look at barium sulfate, which is insoluble, and we put it into water, very few of the barium sulfate compound will dissociate into its ions. The KSP expression that we use for this is based on the law of mass action, and you remember that the law of mass action excludes solids. So the KSP expression just has the aqueous portions of the equations. Let's write KSP expressions for the following. Calcium phosphate is of limited solubility, but when it does dissolve, it breaks apart into 3 calcium ions and 2 phosphate ions. The KSP expression would exclude the solid, and it would show us the calcium ion, and we recall the law of mass action takes the coefficient and turns it into the exponent. So our law of mass action, our equilibrium expression, would take this form. Silver chromate, when it dissolves, breaks into 2 silver ions and 1 chromate ion. Its equilibrium expression shows the silver ion being raised to the 2nd power and the chromate ion to the 1st. It says here that calcium phosphate is added to water until at 25 degrees C until equilibrium is established. So when we write that on our rice table, because I know we're going to need it, we know that it breaks into 3 calcium plus 2 ions and 2 phosphate minus 3 ions. It says equilibrium is established, and when equilibrium is established, the concentration of the calcium plus 2 ion is 3.42 times 10 to the negative 7th molar. Just one small digression about rice tables. Here is the reaction. These are the initial concentrations. This is the change that must occur according to the stoichiometry to get to equilibrium, and E is an equation or a variable that will allow us to figure out the equilibrium.
Stop, this is Eileen again. Sorry to keep on interrupting. Mr. Smith will sign out between 1 and 3 p.m. today. I'll sign out along with Mr. Smith if I have to. If you don't do fundraisers with me, then you can end Amy out so you don't have to stop by. But Mr. Smith will sign out between 1 and 3. After 3 p.m., the office will be closed because we're heading to prepare for graduation. So if you have not signed up by 3 p.m. this afternoon, then you will need to come back on Monday. Thank you. Bye.
Remember that the calcium phosphate initial concentration is not important, nor do we know it. It's not an equilibrium expression, so I will let a question mark stand in for its concentration. It will be of limited solubility for every 1 calcium phosphate unit that dissolves. There will be 3 calcium ions formed and 2 phosphate ions formed. So at equilibrium, the concentration of calcium phosphate, the solubility of calcium phosphate will be X. We know what the ion concentration of the calcium and the phosphate ions will be 2X. So I can now see that X, according to this, can be found because 3X was my change that had to occur to get to equilibrium for my calcium ions, and we have defined my concentration at equilibrium to be this value. So X is equal to 1.14 times 10 to the negative 7. If I multiply X by 2, that will give me 2.28 times 10 to the negative 7, and that will be equal to my phosphate ion concentration. This is my calcium ion concentration. I can then put it into my law of mass action, my KSP expression. We recall that we defined that a little earlier, and it looked like this. So KSP is equal to my calcium ion molarity, 3.42 times 10 to the negative 7, raised to the third power, times my phosphate ion molar concentration, raised to the second power. When I do my math, I find my KSP value is a very small 2.08 times 10 to the negative 33. Very little of this calcium phosphate will dissolve at 25 degrees C. Let's take a moment to go through some vocabulary regarding solutions. A saturated solution is one that contains undissolved solute in contact with the solvent. You remember a saturated solution has dissolved all it possibly can dissolve. Now that we know a little more about equilibrium, a saturated solution is a solution at equilibrium. And we can see that a solution at equilibrium has the forward rate of dissolution equal to the reverse rate of crystallization to be the same. You recall solubility graphs from earlier in the year. On the y-axis, you had the amount of solute in some volume of solvent that would dissolve at every temperature. And we frequently had many lines on there. So this would be the solute, and what you would do is at each temperature you would figure the number of grams that would dissolve. The molar solubility is nothing more than taking the grams of solute that would dissolve in a given amount of solvent and dividing that by its molar mass. The concentration of ions in solution would be this in our previous problem, and KSP would be this expression, and we would treat it like any other equilibrium constant. At the end of this lesson, I expect you to be able to go back and forth from all of these values without too much difficulty. We'll do one problem and end it there. The KSP for silver chromate is 1.12 times 10 to the negative 12. So the KSP expression would be 1.12 times 10 to the negative 12. And that would be equal to the silver ion raised to the second power times the chromate ion raised to the first power. We recall this expression from earlier in this discussion. So silver chromate is a solid, and a saturated solution will have it in equilibrium with its ions. It looks like this. We know there is some amount of silver chromate, and the amount doesn't matter, that will be put into the solvent, and at time equals 0, there will be no ions in the solvent. In order for equilibrium to occur, for every one of these that dissolves, two ions will be formed of silver and one ion of the dichromate, of the chromate. So in equilibrium, we can find the molar solubility of silver chromate to be X. The ion concentration of silver to be 2X, silver ion, and X would cover the chromate ion. So we have let X be the concentration. We can solve for X using the KSP expression that we have identified. So the silver ion is represented by 2X, and we square that. The chromate ion is represented by X. 2X squared is equal to 4X squared times X gives us 4X cubed is equal to 1.12 times 10 to the negative 12. If I divide both sides by 4 and then take the cube root, I will solve for X, and X is equal to 6.54 times 10 to the negative 5th, and that would be molar, and in KSP we generally say moles per liter. That is the molar concentration at 25 degrees C for this particular reaction. That is the answer to this question. Now it says what's the solubility. Remember, when we say solubility, generally we mean grams per liter. That's just a conversion. I would like to know the number of grams per liter equal to 6.54 times 10 to the negative 5th moles per liter of silver chromate. 1 mole of silver chromate has a molar mass of 332 grams. That gives me a solubility of 0.0217 grams of silver chromate will dissolve